Hello, Sir Jude. Today, our group will be discussing composite design patterns. Our group members are Jeremy Ponto, Kevin Herman, and myself, Patrick Elvin. So, what is a composite design pattern? Well, by definition, a composite design pattern in software engineering is a partitioning design pattern. The composite pattern describes a group of objects that are treated the same way as a single instance of the same type of object. The intent of a composite is to compose objects into tree structures to represent part-whole hierarchies. Implementing the composite pattern lets clients treat individual objects and compositions uniformly. So let's ask ourselves, what is an example of a composite design pattern? Well, usually, armies of most countries are structured as hierarchies. An army consists of several divisions. A division is a set of brigades, and a brigade is consisting of platoons, which can be broken down into squads. Finally, a squad is just a small group of real soldiers. Orders are given at the top of the hierarchy and passed down onto each level until every soldier knows what's to be done. So you might be asking yourself, what are the uses of a composite design pattern? Well, two uses is one, the composite pattern when you have to implement a tree-like object structure. The composite pattern provides you with two basic element types that share a common interface, simple leaves and complex containers. A container can be composed of both leaves and other containers. This lets you construct a nested recursive object structure that resembles a tree. The second use is when you use the pattern when you want the client code to treat both simple and complex elements uniformly. All elements defined with the composite pattern share a common interface. Using this interface, the client doesn't have to worry about the concrete class of the object it works with. Now, how do you implement such a design pattern? Well, first off, make sure that the core model of your app can be represented as a tree structure. Try to break it down into simple elements and containers. Remember that containers must be able to contain both simple elements and other containers. Second, declare the component interface with a list of methods that make sense for both simple and complex components. Third, create a leaf class to represent simple elements. A program may have multiple different leaf classes. Fourth, create a container class to represent complex elements. In this class, provide an array field for storing references to sub-elements. The array must be able to store both leaves and containers, so make sure it's declared with the component interface type. While implementing the methods of the component interface, remember that a container is supposed to be delegating most of the work to sub-elements. And finally, define the methods for adding and removal of child elements in the container. Keep in mind that these operations can be declared in the component interface. This would violate the interface segregation principle because the methods will be empty in the leaf class. However, the client will be able to treat all the elements equally, even when composing the tree. Now next, this is just the structure of a design pattern. In the UML class diagram just now, the client class doesn't refer to the leaf and composite classes directly. Instead, the client refers to the common component interface and can treat leaf and composite uniformly. The leaf class has no children and implements the component interface directly. The composite class maintains a container of the child component classes and forwards requests to these children for each child in the children-child operation. The object collaboration diagram shows the runtime interactions. In this example, the client object sends a request at the top of a composite object of type component in the tree structure. The request is forwarded all child components and downwards to the tree structure. Now to go further in depth into this topic, Jeremy will continue on after this.
Let's take a look at these UML class diagrams for a while. So there are two design variants for defining and implementing child-related operations like adding or removing a child component to or from the container. Add child or remove child. The examples of adding or removing a child component to or from the container and accessing a child component, which is getChild for example. The first one is designed for uniformity. which is child-related operations are defined in the component interface. This enables clients to treat leaf and composite objects uniformly. But type safety is lost because clients can perform child-related operations on leaf objects. The other one is designed for type safety. Child-related operations are defined only in the composite class. Clients must treat leaf and composite objects differently. But type safety is gained because clients cannot perform child-related operations on leaf objects. So here is the detailed UML class diagram for the design for type safety variant. First is the component interface, which is the abstraction for all components, including composite ones, and declares the interface for objects in the composition as well as defines an interface for accessing a component's parent in the recursive structure and implements if that's appropriate. This criteria is actually optional. You can use this or not. It's up to the developer or the UML class designer. Second is the leaf class, which represents leaf objects in the composition. Implements all component methods. The last one is a composite class, which represents a composite component, or in other words, component having children. Implements method to manipulate children, and implements all component methods, generally by delegating them to its children. So here we have a sample code which is written in Java. For the composite class, we need to import java.util.arraylist for storing the graphics. First, we declare an interface named graphic, which has a function named print. Later, this function will be overridden by the leaf and composite objects. The second, we have the class name composite graphic, which implements graphic. This class has an instance variable, which is an array list named child graphics that consists of one or more graphics. This class contains the add function for adding graphic, or n print function for printing each graphics inside the array list. Last, we have the leaf class, which implements the graphic interface also. This is a leaf object, so it won't be stored in a composite object. There will be no array list declared here. So we can directly print, in this case, ellipse. The next part, which is the driver code of these codes, will be explained by Kevin.
As Jeremy said, I will explain the what we call the main part here, where the program starts. So this is the main program. I call the class composite demo, and initialize for ellipses, and that I create two composites containing the ellipses. So as we can see here, composite graphic, graphic 2, new composite graphic, and I add ellipse 1, ellipse 2, ellipse 3. Remember in the previous part that Jeremy explained, every ellipse contain one uh, string if you want to print it. It's called the ellipse string. And I also create composite graphic 3, a new composite graphic from that class, and then I add graphic 3, I add ellipse 4 that I create above here. And next, as we can see, I create another graphic contains two graphics, graphics 2 and graphics 3. And that when I print the graphic, four strings ellipse that Jeremy explained before, the string ellipse will be printed. So the sample problem, imagine that you have two types of objects, products and boxes. A box can contain several products as well as a number of smaller boxes. These little boxes can also hold some products or even smaller boxes and so on and so forth. Solution: for a product, it simply return a product's price. For a box, it go over each item the box contains, asks its price, and then return a total for this box. If one of these items were a small box, that box will also start going over its contents, and so on. until the prices of all inner components were calculated. A box could even add some extra cost to the final price, such as packaging cost. Advantage: you can work with complex tree structures more conveniently. Use polymorphism and recursion to your advantage. The second advantage is like open or close principle. You can introduce new element types into the app without breaking the existing code, which now works with the object tree. And here are the disadvantages. It might be difficult to provide a common interface for classes whose functionality differs too much. In certain scenarios, you'd need to overgeneralize the component interface, make it harder to comprehend. So for example, like a new programmer, they will be hard to what do we call it? To understand how the code works if we use too much of this composite design pattern. And okay, here's the resources. Thank you very much and goodbye.